Imagine standing on a beach, watching waves crash against the shore. You feel your feet pressing into the sand. You see the moon hanging in the twilight sky. And connecting all of this, invisible but undeniable, is gravity. The force that holds you to the earth, that pulls the ocean into tides, that keeps the moon circling our planet, and our planet circling the sun. For most of human history, gravity was just a fact of life. Things fall down. That's how the world works. But the truth turned out to be far stranger and more beautiful than anyone imagined. Gravity isn't really pulling you downward at all. It's not even a force in the traditional sense. It's something far more fundamental, a property of space and time itself. And here's what makes this fascinating. Even after centuries of study, we're still discovering new aspects of gravity that challenge everything we thought we knew. From Einstein's revelations about curved spacetime to the recent detection of gravitational waves from colliding black holes, gravity keeps surprising us. It's simultaneously the most familiar force in our daily lives and one of the deepest mysteries in physics. If you enjoy this exploration into one of nature's greatest puzzles, a quick like or subscribe helps the channel continue making content like this. Now let's dive into the strange, beautiful reality of what gravity actually is. The year is 1666. England is gripped by plague, and a young Cambridge student named Isaac Newton has retreated to his family's manor in Woolsthorpe. He's 23 years old, brilliant but unknown, and he's about to have insights that will reshape humanity's understanding of the cosmos. The popular story says an apple fell from a tree, striking Newton and inspiring his theory of gravity. That's probably not exactly what happened, but Newton himself later confirmed that watching apples fall in his garden did spark a crucial question. If gravity pulls the apple down, how far up does that force extend? Does it reach the moon? This was a revolutionary question because in Newton's time, people believed the heavens operated under completely different rules than Earth. The planets and stars were thought to be perfect, eternal, governed by divine principles that had nothing to do with mundane earthly phenomena like falling objects. Newton thought differently. He worked out the mathematics and realized something profound. The same force pulling the apple to the ground also keeps the moon in orbit around Earth. The moon is constantly falling toward our planet, but it's also moving sideways fast enough that it keeps missing. That's what an orbit is, perpetual free fall. In 1687, Newton published his masterwork, usually just called the Principia. In it, he laid out his law of universal gravitation. Every object in the universe attracts every other object with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. Let me break that down. You and Earth pull on each other strongly because Earth is massive. You and a pencil across the room also pull on each other, but so weakly you'd never notice. How weak? If you tried to build a detector sensitive enough to measure the gravitational attraction between two people standing a meter apart, the pull would be less than the weight of a single bacterium. Gravity is absurdly weak compared to other forces. A tiny magnet can overcome the gravitational pull of the entire Earth when it picks up a paperclip. But gravity has one crucial advantage. It always attracts, never repels. And it acts on everything with mass. So while electromagnetic forces cancel out when positive and negative charges balance, gravity just keeps adding up. Get enough mass together, and gravity becomes the dominant force in the universe. Newton's equations worked beautifully. They explained planetary motion with stunning accuracy. They explained tides, the rise and fall of oceans caused by the moon's gravity tugging on Earth's water. They explained why planets farther from the sun move more slowly in their orbits. They even allowed scientists to discover new planets by observing tiny irregularities in the orbits of known ones. That's how Neptune was discovered. In 1846, astronomers noticed Uranus wasn't moving exactly as Newton's equations predicted. They calculated where an unknown planet would need to be to cause those deviations. They pointed their telescopes at that spot in the sky, and there was Neptune, right where the math said it should be. Think about what that means for a moment. Mathematicians sitting at desks with paper and pencil, using only Newton's equations, predicted the existence and location of a planet no one had ever seen. Then astronomers pointed their telescopes at that precise spot in the vast darkness of space and found it. It's hard to overstate how powerful that demonstration was. It showed that mathematics could reveal hidden truths about the universe, that human minds could understand the cosmos through reason and calculation. For over 200 years, Newton's laws seemed to be the final word on gravity. Scientists used them to calculate the orbits of asteroids and comets with incredible precision. Engineers used them to design bridges and buildings. The equations became so trusted that when observations didn't match predictions, astronomers assumed their observations were wrong, or that some unknown factor was at play. But there was a small problem that wouldn't go away, and it involved the planet Mercury, the closest world to our Sun. Mercury orbits in an ellipse that slowly rotates over time. This rotation is called precession, and it happens to all planets to some degree. Newton's equations predicted how much Mercury should precess based on gravitational influences from other planets, particularly Venus and Jupiter, pulling on it as they all orbit the Sun. But observations didn't match. Mercury was precessing about 43 arcseconds more per century than predicted. That's an incredibly small discrepancy, roughly 1/1800th of a degree per century. To put that in perspective, if you drew a circle and then drew another circle that was rotated by 43 arcseconds, you'd need a microscope to see the difference. But it was real, measurable, and unexplained. Scientists searched desperately for answers. Maybe there was an undiscovered planet between Mercury and the Sun, which they named Vulcan. Astronomers spent decades searching for it during solar eclipses, when a planet close to the Sun might become visible. Some even claimed to have seen it. But these sightings could never be confirmed, and no such planet existed. Maybe Newton's laws needed slight adjustments at very close distances to the Sun. Mathematicians tried various modifications. Nothing worked. Maybe there was dust or debris between Mercury and the Sun affecting its orbit. Calculations showed this couldn't account for the discrepancy. The mystery remained unsolved for decades, a tiny crack in the otherwise perfect edifice of Newtonian physics. Then came Albert Einstein. In 1905, Einstein published his special theory of relativity, which showed that space and time are not separate, absolute things. They're woven together into a four-dimensional fabric called spacetime. Nothing can travel faster than light, and time itself can pass at different rates depending on how fast you're moving. But special relativity had a problem. It didn't include gravity. Gravity, in Newton's formulation, acted instantaneously across any distance. If the Sun suddenly disappeared, Earth would immediately fly off in a straight line. But special relativity said nothing can travel faster than light, including information about changes in gravitational fields. So Einstein spent the next 10 years working on a theory that would incorporate gravity into his relativistic framework. The result, published in 1915, was general relativity, one of the most profound insights in the history of science. Einstein's breakthrough was realizing that gravity isn't a force pulling objects together. Instead, massive objects curve the fabric of space-time itself, and other objects follow the curves. It's as if space itself has hills and valleys, and objects naturally roll along the contours. Think of space-time like a stretched rubber sheet. Place a bowling ball on it, and the ball creates a depression. Roll a marble near the bowling ball, and the marble curves toward it. not because the bowling ball is pulling it, but because the marble is following the curved surface of the sheet. Now, this analogy has limits. The rubber sheet is a two-dimensional surface bending in three-dimensional space. But space-time is four-dimensional and isn't bending into anything external. It's intrinsically curved, meaning the curvature is a property of space-time itself. Also, in the rubber sheet analogy, we're using gravity itself to make the ball sink into the sheet. That's circular reasoning when we're trying to explain gravity. So, the analogy is useful for visualization, but don't take it too literally. But the basic idea holds. Massive objects warp spacetime, and that warping is what we experience as gravity. In flat space, the shortest distance between 2 points is a straight line. But in curved space, straight lines don't exist in the usual sense. Instead, there are geodesics, paths representing the shortest distance in that curved geometry. On Earth's surface, which is curved, the shortest path between two cities isn't a straight line through the air. If you have to stay on the surface, it's a curve called a Great Circle route. Flights from New York to Tokyo go over Alaska because that's actually the shortest path on a globe, even though it looks wrong on a flat map. You can test this yourself with a globe and a piece of string. Stretch the string tight between New York and Tokyo on a globe, and you'll see it goes over the Arctic, not across the Pacific as you might expect from looking at a flat map. In curved spacetime, objects follow geodesics. A planet orbiting the Sun isn't being pulled by a force. It's following the straightest possible path through the curved spacetime created by the Sun's mass. From the planet's perspective, it's moving in a straight line. But because spacetime is curved, that straight line looks like an orbit from our perspective. The planet is constantly falling toward the Sun, but also moving sideways fast enough that it keeps missing it, a perpetual state of free fall. This is why astronauts in orbit feel weightless. They're not beyond Earth's gravity. The gravitational field at the International Space Station, which orbits about 400 kilometers above Earth, is still about 90% as strong as on the ground. The astronauts feel weightless because they're in freefall, following a geodesic through curved space-time. The station and the astronauts are falling toward Earth at the same rate, so relative to each other, they float. You experience the same thing briefly when you jump. For that moment in the air, you're in freefall and weightless. You don't feel your weight pressing on your feet. The sensation only returns when the ground interrupts your fall. If you could somehow extend that moment, remove the ground so you kept falling, you'd feel exactly what astronauts feel in orbit. True weightlessness. Picture yourself in an elevator and someone cuts the cable. Terrible scenario, but stick with me. As the elevator falls, you'd float inside it. You wouldn't feel your weight. You'd be in free fall along with the elevator. Alternatively, imagine you're out in deep space, far from any planet or star. You and the elevator are drifting. You'd also float inside because there's nothing to push against. Einstein's insight was that these two situations are equivalent. Freefall in a gravitational field and floating in deep space with no gravity are the same experience. You can't tell the difference from inside the elevator. This is called the equivalence principle, one of the foundational ideas of general relativity. Similarly, standing in an elevator on Earth, you feel the floor pushing up on your feet. That's what weight is, the floor resisting your tendency to follow a geodesic through curved spacetime. In a rocket in deep space, if the rocket is accelerating at 9.8 meters per second squared, the same acceleration you experience from Earth's gravity, you'd feel the floor of the rocket pushing up on your feet in exactly the same way. From inside the rocket, there's no experiment you could do to tell whether you're standing on Earth or accelerating in deep space. These two situations are equivalent. The equivalence principle leads to some strange predictions. One is gravitational time dilation. Time passes at different rates depending on where you are in a gravitational field. The stronger the field, the slower time passes. If you're standing on the surface of a massive planet where space-time is highly curved, time passes more slowly for you than for someone in orbit where space-time is less curved. This isn't a perceptual thing, not that time feels slower. Time actually passes at different rates. If you had two synchronized clocks and put one on the surface and one in orbit, when you brought them back together, they'd show different times. The one on the surface would show less time had passed. This has been measured experimentally many times. In 1971, scientists put extremely accurate atomic clocks on commercial airplanes and flew them around the world. When they landed, those clocks were ahead of identical clocks that stayed on the ground by exactly the amount predicted by general relativity. The difference was tiny, measured in nanoseconds, but it was real and measurable. GPS satellites orbiting Earth have to account for time dilation, or their position calculations would be off by kilometers within hours. The atomic clocks on GPS satellites run slightly faster than clocks on Earth's surface because they're higher up where space-time is less curved. The GPS system corrects for this automatically. Every time you navigate with your phone, you're relying on Einstein's predictions being accurate. General relativity also predicts gravitational lensing. Light follows geodesics through curved space-time just like everything else. So if light passes near a massive object, its path will curve. A massive object can act like a lens, bending light that passes near it. This was first observed in 1919 during a solar eclipse. Astronomers photographed stars near the sun during the eclipse. When the sun's glare didn't overwhelm the starlight, they found that stars appeared slightly displaced from their known positions. The sun's gravity was bending the starlight passing near it, making the stars appear in slightly different positions. The amount of displacement matched Einstein's predictions precisely. This observation made Einstein world famous overnight. The story of that eclipse expedition is worth telling because it captures a remarkable moment in history. This was 1919, just after World War I had ended. Einstein was German, and the astronomers planning to test his theory were British. The war had created enormous hostility between the nations. Yet here was British science mounting an expensive expedition to test a German scientist's radical theory. Two teams went out, one to Sobral in Brazil, and one to Principe, an island off the coast of West Africa. They photographed the eclipse and measured the positions of stars near the sun's edge. When they returned and analyzed the photographic plates, comparing star positions during the eclipse to positions when the sun wasn't nearby, they found exactly the deflection Einstein had predicted. When the results were announced at a joint meeting of the Royal Society and the Royal Astronomical Society in London, it made front-page news around the world. The New York Times headline read, "Lights all askew in the heavens, men of science more or less agog." Today, gravitational lensing is a standard tool in astronomy. When light from a distant galaxy passes near a massive object, like a galaxy cluster between us and that distant galaxy, the light gets bent. Sometimes the light takes multiple paths around the massive object, and we see multiple images of the same distant galaxy. Or the galaxy gets stretched into arcs or rings. By studying these lensed images, astronomers can map the distribution of mass in the lensing object, including dark matter, which we can't see directly, but which still curves space-time. Some of the most beautiful images from the Hubble Space Telescope show this gravitational lensing in action, with distant galaxies stretched and distorted into luminous arcs around massive foreground clusters. Black holes are the most extreme example of curved space-time. A black hole is a region where space-time is so severely curved that nothing, not even light, can escape. The boundary of no return is called the event horizon. Once you cross it, all possible paths through space-time lead inward toward the center. There's no way out, not because something is pulling you in, but because space-time itself is curved so extremely that all geodesics point inward. Black holes form when massive stars collapse at the end of their lives. A star is a balance between gravity trying to compress it and pressure from nuclear fusion pushing outward. As long as the star is fusing hydrogen, helium, or heavier elements in its core, the pressure keeps the star from collapsing. Eventually, a massive star runs out of fuel. The fusion stops. The outward pressure disappears. Gravity wins. The star collapses. If the star is massive enough, more than roughly 20 times the mass of our Sun, the collapse doesn't stop. The entire star compresses into an infinitely small point called a singularity. Around that singularity is the event horizon. The size of the event horizon depends on the mass. For a black hole with the mass of our Sun, the event horizon would be around 3 kilometers in radius. That's called the Schwarzschild radius, after Karl Schwarzschild, who calculated it in 1916, just months after Einstein published general relativity. Schwarzschild was actually serving as a German artillery officer during World War I when he worked out these equations. He sent them to Einstein from the Russian front. Tragically, Schwarzschild died just a few months later from a disease he contracted in the trenches, never knowing how important his solution would become. For a black hole with 10 solar masses, the radius would be roughly 30 kilometers. For a supermassive black hole with 1 billion solar masses, like the ones at the centers of galaxies, the radius would be nearly 3 billion kilometers, larger than the orbit of Saturn. Think about that for a moment. The supermassive black hole at the center of our galaxy has an event horizon larger than our entire solar system out to Saturn's orbit. Yet all that mass is compressed into that region, creating space-time curvature so extreme that not even light can escape. From the perspective of someone falling into a black hole, they cross the event horizon in finite time. They'd fall through in seconds or minutes or hours depending on the black hole's mass. But from the perspective of someone watching from outside, the falling person never quite reaches the event horizon. As the person approaches the horizon, time dilation becomes more and more extreme. Time passes slower and slower for the falling person relative to the outside observer. The light from the falling person becomes increasingly red-shifted, shifting from visible light to infrared to radio waves, becoming dimmer and dimmer. Eventually, the person appears to freeze just outside the event horizon, fading from view like the Cheshire Cat, becoming redder and dimmer until they vanish entirely. But this is just a perspective effect, an illusion created by the extreme warping of space-time. The person themselves experiences falling through normally, crossing the horizon without any special sensation at that moment. Inside the event horizon, space-time is so warped that the future points toward the center. Just as surely as your future in normal space-time points forward in time, your future inside a black hole points toward the singularity. You can no more avoid hitting the singularity than you can avoid moving forward in time. The singularity isn't a place in space you can avoid by moving sideways. It's a moment in your future that you will inevitably reach. At the singularity, space-time curvature becomes infinite. Matter is compressed to infinite density, and our current theories break down. General relativity predicts the singularity, but can't describe what happens there because the math gives infinities, which usually means the theory has reached its limits. Most physicists think that quantum effects, which general relativity doesn't include, become important at some point before you reach the true singularity. But we don't have a complete theory of quantum gravity yet, so we can't say for sure what happens at the very center of a black hole. The singularity raises profound questions about the nature of space-time itself. Is infinite curvature physically real, or does it signal that our description fails? Some physicists think space-time itself might dissolve at the Planck scale, approximately 10 to the minus 35 meters, replaced by something more fundamental, perhaps a quantum foam where space and time lose their classical meaning. The singularity might not be a point of infinite density, but rather a region where our concepts of space and time simply stop applying. There's also the cosmic censorship conjecture proposed by Roger Penrose. It states that all singularities are hidden inside event horizons, invisible to outside observers. Nature seems to enforce this rule. We don't see naked singularities, singularities without event horizons. Why? If naked singularities existed, light from them could reach us, and we'd observe regions where physical laws break down, where predictability fails. The universe would have visible flaws in its causal structure. Cosmic censorship protects us from this chaos, though we don't fully understand why nature enforces it. Some extreme scenarios, like colliding black holes or rapidly spinning black holes, might briefly create naked singularities before they're covered by event horizons. These scenarios are active areas of research, testing whether cosmic censorship always holds or has loopholes. There's a lot of misconception about black holes. People think they're like cosmic vacuum cleaners, sucking in everything around them. That's not true. A black hole only pulls on things gravitationally, just like any other object with mass. If our sun suddenly became a black hole with the same mass, which it won't because it's not massive enough, Earth's orbit wouldn't change. We'd still orbit at the same distance. We'd freeze because the sun wouldn't be radiating light and heat anymore, but we wouldn't get sucked in. You only get into trouble with a black hole if you get very close, closer than you could get to a normal star, because the star's physical surface would be in the way. With a black hole, the physical matter has collapsed inside the event horizon, so you can get much closer to the center of mass. That's when the tidal forces become extreme. Tidal forces are differences in gravitational pull across an object. Earth's tides are caused by the moon pulling slightly harder on the side of Earth facing it than on the side facing away. With normal objects like Earth or the moon, tidal forces are gentle, but near a black hole, they become savage. If you fell feet first toward a black hole, your feet would be closer to the black hole than your head. The pull on your feet would be stronger than the pull on your head. The difference would stretch you. As you got closer, the stretching would become more and more extreme. Eventually, you'd be pulled apart, stretched like spaghetti. Physicists have a term for this: spaghettification. It's a real term used in technical papers. For a small black hole, spaghettification would happen before you even reach the event horizon. The tidal forces just outside the horizon would be strong enough to tear you apart. For a supermassive black hole, the event horizon is so far from the center that tidal forces at the horizon are relatively gentle. You could cross the event horizon without immediately being torn apart. You'd only get spaghettified much later as you fell closer to the singularity. This is counterintuitive, but true. You'd have a better chance of surviving longer falling into a supermassive black hole than a small one, at least until you got much deeper inside. Black holes aren't completely black. In 1974, Stephen Hawking predicted that black holes emit radiation due to quantum effects near the event horizon, now called Hawking radiation. The basic idea is that empty space isn't truly empty. Quantum mechanics tells us that particle-antiparticle pairs are constantly popping into existence and then annihilating each other almost immediately. This normally doesn't lead to anything observable because the particles exist for such a brief time. But near a black hole's event horizon, something interesting can happen. One particle of the pair might fall into the black hole while the other escapes. From outside, it looks like the black hole is emitting radiation. This radiation carries energy away from the black hole, so the black hole gradually loses mass and shrinks over time. Black hole evaporation. The effect is incredibly slow for large black holes. A black hole with the mass of our Sun would take about 10 to the 67th years to evaporate completely. That's a 1 followed by 67 zeros. For comparison, the universe is only about 13.8 billion years old, roughly 10 to the 10th years. So a solar mass black hole would take vastly longer than the current age of the universe to evaporate. For supermassive black holes, the evaporation time is even longer, far beyond any meaningful timescale. But for tiny black holes, if they exist, evaporation could be fast. A black hole with the mass of a mountain would evaporate in about 1 billion years. A black hole with the mass of a car would explode in a fraction of a second, releasing energy equivalent to multiple nuclear bombs. Fortunately or unfortunately, depending on your perspective, we've never observed any primordial black holes of such small size, and we don't know if they exist. If they do exist, they might have formed in the very early universe when conditions were extreme enough to compress small regions into black holes. Some physicists have speculated that primordial black holes could account for some or all of dark matter, but searches for them through gravitational lensing and other effects have so far come up empty. Hawking radiation is one of the most important predictions at the intersection of quantum mechanics and gravity. It suggests that black holes aren't eternal, that they eventually evaporate away completely. This raises profound questions about what happens to the information that fell into the black hole. According to quantum mechanics, information can't be destroyed. But if a black hole evaporates completely, where does the information go? This is called the black hole information paradox, and it's been one of the hottest topics in theoretical physics for decades. Stephen Hawking originally argued that information is genuinely lost, that black holes are the one place where quantum mechanics breaks down. This created an uproar in the physics community. Many physicists found this unacceptable because information conservation is such a fundamental principle of quantum mechanics. For decades, theorists battled over the paradox. In the early 2000s, Hawking conceded he was probably wrong, proposing that information might be encoded in subtle correlations in the Hawking radiation emitted by black holes. But how exactly this works mathematically remains unclear. Recent work suggests the information might be encoded at the event horizon itself in a holographic manner. The holographic principle proposes that all the information about a three-dimensional volume of space can be encoded on its two-dimensional boundary, like a hologram. For a black hole, the horizon acts as this boundary. Information about everything that fell in might be preserved in the horizon structure, gradually released as the black hole evaporates through Hawking radiation. This would preserve unitarity, the quantum mechanical principle that information is conserved, but it requires quantum gravity to fully understand, and we don't have that complete theory yet. Gravitational waves are one of the most spectacular confirmations of general relativity. According to Einstein's theory, accelerating masses produce ripples in space-time itself, traveling outward at the speed of light and carrying energy away from their source. Imagine throwing a rock into a pond. Ripples spread out across the water's surface. Gravitational waves are similar, except they're ripples in the fabric of space-time itself. As a gravitational wave passes through a region of space, it alternately stretches and squeezes that space in perpendicular directions. The effect is minuscule. When gravitational waves from colliding black holes pass through Earth, they change distances by less than the width of a proton, over distances of several kilometers. Einstein predicted gravitational waves in 1916, but thought they'd be far too weak to ever detect. For decades, they remained purely theoretical curiosities, mathematical predictions that most physicists assumed would never be directly observed. Then in the 1970s, astronomers Russell Hulse and Joseph Taylor discovered a binary pulsar, two neutron stars orbiting each other. A pulsar is a rapidly rotating neutron star that emits beams of radio waves from its magnetic poles. As it rotates, these beams sweep across space like a lighthouse. If one of the beams points toward Earth, we see regular pulses of radio waves, hence the name pulsar. Some pulsars are incredibly precise timekeepers, more accurate than the best atomic clocks. Hulse and Taylor found a pulsar in orbit with another neutron star. By timing the pulsar's pulses with extraordinary precision, they could measure tiny changes in the orbit. They observed that the orbit was gradually decaying. The two stars were slowly spiraling inward. The rate of decay matched exactly what you'd expect if the system was losing energy to gravitational waves. This was indirect evidence that gravitational waves exist, exactly as Einstein predicted. Hulse and Taylor won the Nobel Prize for this discovery in 1993. Their work showed that gravitational waves were real, but detecting them directly still seemed impossibly difficult. In the United States, scientists built the Laser Interferometer Gravitational Wave Observatory, called LIGO. It's one of the most ambitious and precise scientific instruments ever constructed. LIGO consists of two facilities, one in Louisiana and one in Washington State, separated by about 3,000 kilometers. Each facility has two arms 4 kilometers long, arranged in an L shape. Laser beams bounce back and forth along these arms. If a gravitational wave passes through, it stretches space in one direction and squeezes it in the perpendicular direction, changing the length of the arms by a minuscule amount. The two facilities are positioned far apart so that scientists can verify that any signal they detect is real and not just local noise or vibration. The precision required is almost incomprehensible. When LIGO made its first detection, the change in arm length was about 1/10,000th, the diameter of a proton. To put that in perspective, if you scaled up an atom to the size of the solar system, LIGO would be able to detect a change smaller than the width of a human hair. It's like measuring the distance to the nearest star, over 4 light years away, to within the width of a single strand of hair. The technology required to achieve this precision is extraordinary. The mirrors at the ends of the arms must be polished to incredible smoothness. The laser systems must be stable to 1 part in a billion, and the entire facility must be isolated from vibrations caused by everything from earthquakes to passing trucks to ocean waves hundreds of kilometers away. On September 14, 2015, just days after LIGO began its first observing run after a major upgrade, both detectors picked up a signal. A gravitational wave had swept through Earth. The signal lasted only a fraction of a second, but it was clear and unmistakable, rising in frequency and amplitude before cutting off suddenly. By analyzing the signal, scientists determined it came from 2 black holes, 29 and 36 times the mass of the Sun, spiraling into each other 1.3 billion light years away. As the black holes orbited each other faster and faster, they emitted gravitational waves, losing energy and spiraling inward. In the final fraction of a second, they merged into a single black hole of 62 solar masses. Wait a minute. 29 plus 36 equals 65, not 62. What happened to those 3 solar masses? They were converted entirely into gravitational wave energy, according to Einstein's famous equation E equals mc squared. In that brief moment, the merger released more energy in gravitational waves than all the stars in the observable universe were emitting in light at that same moment. Think about that. The power output during that fraction of a second was roughly 50 times the combined light output of every star in the entire universe. It's almost impossible to comprehend that much energy released so quickly, and yet gravitational waves from such events pass through Earth regularly, stretching and squeezing spacetime by amounts so tiny we can only detect them with our most sophisticated instruments. Since that first detection, LIGO and its European counterpart, Virgo, have detected dozens of gravitational wave events. Most are black hole mergers, but some are neutron star collisions. In August 2017, LIGO and Virgo detected gravitational waves from two neutron stars colliding. This event was also observed with traditional telescopes across the electromagnetic spectrum, from gamma rays to radio waves. It was the first time an astronomical event was observed with both gravitational waves and light, ushering in a new era of multi-messenger astronomy where we study cosmic events using different kinds of signals. The neutron-star merger was particularly important because it showed that these collisions are the cosmic forges where heavy elements like gold and platinum are created. The explosion scattered these elements across space, enriching future generations of stars and planets. What makes gravitational wave astronomy revolutionary isn't just detecting these events. It's what we learn from them. When neutron stars merge, the gravitational wave signal encodes information about their internal structure. Neutron stars are laboratories for extreme physics, with matter compressed to densities where atomic nuclei merge into exotic states. Different theories about how matter behaves under these conditions predict slightly different gravitational wave signatures during a merger. By analyzing the waves, we're essentially probing the interior structure of neutron stars, conducting experiments on matter at nuclear densities that we could never achieve on Earth. These observations also test fundamental physics. The speed of gravitational waves equals the speed of light to extraordinary precision, just as general relativity predicts. Some alternative theories of gravity predicted different speeds. The observations rule out entire classes of modified gravity theories. Gravitational waves also offer a unique way to measure cosmic distances. The amplitude of the wave tells us how far away the source is, while the frequency evolution tells us the masses of the merging objects. If we can also identify the host galaxy with traditional telescopes, we can measure both the distance and the galaxy's recession velocity, giving us an independent measurement of the universe's expansion rate. This is potentially crucial because there's currently a tension in cosmology. Different methods of measuring the expansion rate give slightly different answers, and we don't know why. Gravitational wave cosmology might help resolve this tension by providing a completely independent way to measure distances. Gravitational waves give us a completely new way to observe the universe. Light can be blocked by dust or gas, but gravitational waves pass through matter almost unimpeded. They carry information about events we could never see with traditional telescopes, like the insides of supernovas or the very early universe moments after the Big Bang. When a massive star explodes as a supernova, most of the energy is carried away by neutrinos and gravitational waves, not light. Future gravitational wave detectors might detect waves from supernovas in our galaxy, giving us information about the explosion mechanism that we can't get any other way. In the coming decades, even more sensitive gravitational wave detectors will be built. LIGO is being upgraded continuously, and new detectors are being built in Japan and India. These will form a global network capable of pinpointing the sources of gravitational waves much more precisely. The Laser Interferometer Space Antenna, called LISA, is planned for the 2030s. It will consist of 3 spacecraft arranged in a triangle with sides 5 million kilometers long, orbiting the Sun. LISA will detect lower frequency gravitational waves from sources like supermassive black holes merging at the centers of galaxies, events LIGO can't detect because it's designed for higher frequencies. LISA might even detect gravitational waves from the Big Bang itself, ripples in spacetime produced in the first moments of the universe's existence. When astronomers study galaxies, they measure how fast stars orbit the galactic center. Based on the visible matter, stars on the outer edges should move much slower than they actually do. According to Newton's laws and general relativity, the orbital speed should decrease as you move farther from the center, just like planets farther from the Sun orbit more slowly. But observations show that stars in the outer regions of galaxies move just as fast as stars closer to the center. The only explanation is additional mass we can't see, providing extra gravitational pull. We call this dark matter. It doesn't emit light or any electromagnetic radiation, which is why it's dark. But it has mass, so it curves space-time and affects visible matter through gravity. The evidence for dark matter is overwhelming and comes from multiple independent observations: galaxy rotation curves, gravitational lensing, the cosmic microwave background, the large-scale structure of the universe, collisions between galaxy clusters. All of these point to the existence of dark matter. Roughly 85% of the matter in the universe is dark matter. Only 15% is ordinary matter, the stuff that makes up stars, planets, and people. What is dark matter? We don't know. It's not just dark clouds of normal matter, like planets or dust, because such objects would absorb and block light from objects behind them. Dark matter doesn't do that. It's completely transparent. Leading theories suggest it's made of undiscovered subatomic particles that don't interact with light or normal matter except through gravity. Scientists have proposed several candidates for dark matter particles. WIMPs, or weakly interacting massive particles, are a popular candidate. These would be heavy particles that only interact through gravity and the weak nuclear force. Experiments deep underground are searching for WIMPs by looking for rare collisions with normal atoms. So far, they haven't detected anything conclusive. Axions are another candidate, much lighter particles that would have been produced in enormous quantities in the early universe. Sterile neutrinos, hypothetical cousins of ordinary neutrinos that don't interact via the weak force, are also possibilities. Some physicists even speculate that dark matter might be primordial black holes, microscopic black holes formed in the first moments after the Big Bang. The search for dark matter is one of the most active areas in physics. Detectors are getting more sensitive. Particle physics experiments are looking for dark matter particles produced at accelerators, and astronomical surveys are mapping dark matter's distribution in unprecedented detail. Some experiments claim to have seen hints of dark matter particles, but these results remain controversial and unconfirmed. The mystery deepens because we don't even know if dark matter is one thing or many. There might be multiple types of dark matter particles, forming their own dark sector of physics with its own forces and interactions that we're completely blind to. Dark matter shapes the large-scale structure of the universe. Galaxies form where dark matter is densest. In the early universe, dark matter began clumping together under its own gravity, creating dense regions that attracted ordinary matter. This ordinary matter fell into the gravitational wells created by dark matter, forming the first stars and galaxies. By mapping how galaxies cluster today, astronomers learn about the dark matter distribution that shaped their formation. Computer simulations can model how dark matter structures grow over cosmic time, and these simulations match observations remarkably well when you include dark matter but fail completely without it. Gravitational lensing provides one of the best ways to map dark matter directly. When light from distant galaxies passes through a galaxy cluster, it bends around the cluster's mass, including dark matter. By studying how the light bends and how background galaxies appear distorted, astronomers can create maps showing where dark matter concentrates, even though they can't see it directly. These maps reveal that dark matter forms a cosmic web, a vast network of filaments stretching across the universe. Galaxies gather along these filaments like beads on strings. Where filaments intersect, massive galaxy clusters form. Between the filaments lie voids, vast underdense regions containing few galaxies. One of the most compelling pieces of evidence for dark matter comes from the Bullet Cluster, a collision between two galaxy clusters about 3.8 billion light-years away. When the clusters collided, the hot gas in each cluster interacted, slowing down and staying near the collision site. But gravitational lensing shows that most of the mass, traveled with the clusters themselves, not with the gas. This is exactly what you'd expect if dark matter exists and barely interacts with normal matter. The dark matter in each cluster passed right through without slowing down, while the gas collided and stayed behind. Alternative theories of gravity, which attempt to explain galactic rotation without dark matter, struggle to explain the bullet cluster because they predict that gravity should follow the gas, not the invisible dark matter. In 1998, astronomers studying distant supernovas made a shocking discovery that would reshape our understanding of the universe. The expansion of the universe is accelerating. After the Big Bang, the universe started expanding, and everyone assumed that gravity would gradually slow that expansion over time. The universe might eventually stop expanding and collapse back in a big crunch, or it might expand forever but at a decreasing rate. But acceleration? That suggested something was pushing the universe apart, counteracting gravity. This mysterious something is called dark energy, and it's even more puzzling than dark matter. Dark energy appears to be a property of space itself. As the universe expands, creating more space, there's more dark energy. This drives faster expansion, which creates even more space and even more dark energy, a runaway process. Dark energy makes up roughly 68% of the total energy content of the universe. Dark matter is about 27%. Ordinary matter, everything we can see and touch, is only about 5%. We live in a universe where 95% of it is stuff we don't understand. That should be humbling. The discovery of dark energy came from careful observations of Type Ia supernovas, stellar explosions that serve as standard candles because they have predictable brightness. By measuring how bright they appear, astronomers can calculate their distance. By measuring their redshift, how much their light has been stretched by cosmic expansion, astronomers can determine how fast they're moving away from us. Two independent teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, both found the same surprising result. Distant supernovas were dimmer than expected, meaning they were farther away than they should be if the universe's expansion was slowing down. The only explanation was that the expansion is accelerating. The team's leaders, Saul Perlmutter, Brian Schmidt, and Adam Rees, shared the 2011 Nobel Prize in Physics for this discovery. The existence of dark energy has profound implications for the universe's fate. Because the expansion is accelerating, distant galaxies are moving away from us faster and faster. Eventually, they'll be moving away so fast that their light can no longer reach us. In the far future, trillions of years from now, the universe will be a much lonelier place. Most galaxies will be beyond our cosmic horizon, the distance beyond which light can no longer reach us, because space between us and them is expanding faster than light can travel. Only the galaxies in our local group, held together by gravity into a single structure, will remain visible. The Milky Way, Andromeda, and a few dozen smaller galaxies bound together will eventually merge into a single giant elliptical galaxy. The rest of the universe will have expanded away beyond reach, invisible and unreachable. Civilizations arising in that distant future would look out and see only their own galaxy surrounded by darkness. They'd have no way to know the universe had ever been larger or fuller. Everything we've learned about cosmology, the Big Bang, the expansion of the universe, the cosmic microwave background, would be inaccessible to them. The evidence would have literally expanded away beyond their ability to observe it. We're fortunate to exist at a time when we can still observe and study the broader universe. In a cosmic sense, we live in a special epoch when the universe is old enough to have formed complex structures like galaxies and planets and life, but young enough that we can still see and study its history and large-scale structure. Dark energy poses one of the deepest puzzles in physics. In Einstein's equations, it appears as the cosmological constant, a term Einstein originally added to his equations to keep the universe static, then abandoned when Hubble discovered the universe was expanding. Einstein later called this his greatest blunder, though in an ironic twist, it turns out the cosmological constant might be exactly what we need to explain dark energy. The problem is that when physicists calculate what the cosmological constant should be based on quantum mechanics, they get a number that's wrong by a factor of 10 to the 120 power. That's not a typo. The theoretical prediction is a 1 followed by 120 zeros times larger than the observed value. This is often called the worst prediction in the history of physics. It's such a spectacular failure that it suggests we're missing something fundamental about how gravity and quantum mechanics fit together. Some physicists think the solution involves the multiverse, the idea that our universe is just one of countless universes with different values of physical constants. We naturally find ourselves in a universe where the cosmological constant has a value that allows galaxies and stars and planets and life to exist. In universes where the constant is much larger, the expansion would be so fast that galaxies could never form. Matter would be pulled apart before gravity could clump it together. In universes where the constant is large but negative, the universe would collapse before stars could even form. This anthropic explanation is controversial. Some scientists find it unsatisfying because it gives up on finding a deeper reason why the constant has the value it does. They argue that saying, "We observe this value because if it were different, we wouldn't be here to observe it," isn't really an explanation at all. Others argue it's the most natural explanation given what we know about quantum mechanics and cosmology, and that we should accept it even if it doesn't satisfy our desire for a deeper answer. The debate over dark energy and the cosmological constant touches on deep questions about the nature of explanation in science. What counts as a satisfactory scientific explanation? Is it enough to say that constants have the values they do because those values permit observers to exist? Or must there be a deeper dynamical reason, some underlying mechanism that produces those values? These are not just scientific questions but philosophical ones, touching on the foundations of how we understand the universe and our place in it. For now, dark energy remains profoundly mysterious. We know it's there because we can observe its effects on cosmic expansion, but we don't know what it is or why it has the value it does. Solving this puzzle will likely require new physics beyond both general relativity and quantum mechanics. Gravity shapes the universe on the largest scales. After the Big Bang, matter was distributed almost uniformly, with only tiny variations in density, about 1 part in 100,000. But gravity amplified those tiny variations over billions of years. Slightly denser regions had slightly stronger gravity, pulling in more matter. This made them denser still, pulling in even more matter. Less dense regions lost matter to denser neighbors, becoming even less dense. Over time, this process created the large-scale structure we see today: galaxies, galaxy clusters, superclusters, and the cosmic web. Computer simulations can model this process. They start with initial conditions matching the early universe's density fluctuations, which we can observe in the cosmic microwave background. Then they evolve forward in time using the laws of gravity and cosmology. The results match observations remarkably well, confirming our understanding of how gravity shapes cosmic structure. The Sloan Digital Sky Survey has mapped over 1 million galaxies, revealing the cosmic web in stunning detail. The distribution isn't random. Galaxies trace out filaments and sheets, with enormous voids between them. The pattern looks almost biological, like neurons in a brain or roots of plants spreading through soil. This structure formed through gravity alone, acting on the tiny density variations present in the early universe. Those variations themselves were likely produced by quantum fluctuations during inflation. stretched to cosmic scales by exponential expansion in the first fraction of a second after the Big Bang. In a very real sense, the cosmic web we see today, spanning billions of light years, is a quantum phenomenon written large across the universe. The largest structures in the universe are superclusters, collections of galaxy clusters spanning hundreds of millions of light years. Our Milky Way is part of the Local Group, a collection of about 80 galaxies dominated by the Milky Way and Andromeda. The Local Group is part of the Virgo supercluster, which contains thousands of galaxies. And the Virgo supercluster is part of an even larger structure called Laniakea, which contains about 100,000 galaxies spread across 520 million light-years. The discovery of these vast structures was surprising because they're so large that light hasn't had time since the Big Bang to cross them. Yet they exist, bound together by gravity, suggesting that the seeds of structure were present very early in the universe's history. Remember how gravity is absurdly weak compared to other forces. The electromagnetic force is about 10 to the 36th power times stronger than gravity. That's a 1 followed by 36 zeros. This enormous difference is called the hierarchy problem, and it's one of the deepest puzzles in physics. Why such a vast disparity between gravity and the other forces? One way to see how strange this is, imagine scaling up an atom to the size of the solar system. In this scaled version, the electromagnetic forces holding the atom together would still be vastly stronger than the gravity holding the solar system together. Gravity only becomes dominant when you have enormous amounts of mass, like planets, stars, and galaxies. Several theories attempt to explain this hierarchy. One involves extra dimensions. Our universe might have more than the 3 spatial dimensions we experience. Gravity could be strong in the full, higher dimensional space, but appears weak to us because we're confined to a 3-dimensional brain within that higher dimensional space. Gravity, unlike the other forces, can leak into the extra dimensions, diluting its strength. This idea comes from string theory and suggests that the extra dimensions might be detectable at very high energies or very short distances. Experiments at the Large Hadron Collider have looked for signs of extra dimensions, but so far they've found nothing. Another approach involves supersymmetry, a theoretical symmetry between matter particles like electrons and quarks, and force particles like photons and gluons. Supersymmetry predicts that every known particle has a heavier supersymmetric partner. These particles could help explain the hierarchy by cancelling out certain quantum corrections that would otherwise make gravity much stronger or the other forces much weaker. Despite extensive searches at the Large Hadron Collider and other experiments, these supersymmetric particles haven't been found yet. This doesn't mean supersymmetry is wrong, but it suggests that if supersymmetric particles exist, they're heavier than we expected, possibly too heavy for current experiments to produce. The hierarchy problem connects to another puzzle about the Higgs boson, discovered at the Large Hadron Collider in 2012. The Higgs gives mass to other particles, and its own mass determines the strength of the weak nuclear force. But quantum corrections should push the Higgs mass to incredibly high values, essentially the Planck mass, where quantum gravity effects become important, about 10 to the 19th power gigaelectronvolts. Yet the measured Higgs mass is only about 125 gigaelectronvolts, much lower. Something appears to be protecting the Higgs mass from these quantum corrections, and we don't know what. Supersymmetry was one proposed solution, but with no supersymmetric particles found, physicists are looking at other possibilities. These problems suggest that our understanding of gravity remains incomplete, especially when trying to connect it to quantum mechanics. General relativity describes gravity beautifully on large scales, from planets to galaxies to the entire universe. Quantum mechanics describes the microscopic world of atoms and particles with stunning precision. Both theories work brilliantly in their respective domains, but they're fundamentally incompatible. General relativity is a classical theory where space-time is smooth and continuous. Quantum mechanics is probabilistic, dealing with discrete particles and uncertainty. When you try to apply both to the same situation, like the interior of a black hole or the first instant of the Big Bang, they give contradictory answers. We need a unified theory of quantum gravity, and despite decades of work by some of the brightest minds in physics, we don't have one yet. String theory is one leading candidate. In string theory, particles aren't point-like objects. They're tiny vibrating strings, about the Planck length in size. Different vibration patterns correspond to different particles, like different notes on a violin string. Electrons, quarks, photons, all are different vibrations of the same fundamental strings. The theory naturally includes gravity, because one vibration pattern produces the graviton, the hypothetical particle that mediates the gravitational force. String theory is mathematically beautiful and elegant. It naturally unifies all the forces of nature and includes gravity in a quantum framework. But it has problems. String theory requires extra dimensions, usually 10 or 11 total dimensions. In addition to the 3 spatial dimensions we experience and 1 time dimension, there must be 6 or 7 extra spatial dimensions. Where are they? The standard answer is that they're curled up so small we don't notice them, compactified at scales near the Planck length. But this raises questions. Why are some dimensions large and others small? What determines their sizes and shapes? There are many possible ways to curl up extra dimensions, leading to many possible universes with different physics. String theory also faces what's called the landscape problem. There are roughly 10 to the 500th power possible vacuum states, different ways the theory can be configured. Each corresponds to a different universe with different physical constants, different particle masses, different force strengths. Some physicists embrace this as evidence for the multiverse, arguing that all these universes exist somewhere and we happen to live in one compatible with life. Others see it as a failure to make unique predictions. If string theory can accommodate almost any observation by choosing the right vacuum state, is it really making testable predictions? This has led to heated debates about whether string theory is even science in the traditional sense. Loop quantum gravity takes a completely different approach. Instead of starting with strings, it tries to quantize space-time itself, treating space not as a smooth continuum, but as a network of tiny loops. At the Planck scale, space would be discrete, coming in indivisible chunks like pixels on a screen. Time would also be discrete, advancing in minimum steps. This approach naturally produces a quantum theory of gravity without requiring extra dimensions. It predicts that the singularities in black holes and the Big Bang are replaced by quantum bounces, regions where extreme density triggers a repulsive quantum gravity effect that prevents infinite curvature. Loop quantum gravity has its own challenges. It struggles to recover general relativity smoothly at larger scales. The mathematics is complex and less developed than string theory, and it doesn't naturally incorporate the other forces of nature, focusing only on gravity. Some physicists are working on extensions that include matter and forces, but this remains an active area of research. There are other approaches to quantum gravity as well. Causal dynamical triangulations imagine space-time as built from simple geometric building blocks that evolve according to probabilistic rules. Asymptotic safety proposes that gravity at high energies reaches a fixed point where quantum corrections cancel out. Emergent gravity theories suggest that space-time and gravity aren't fundamental at all, but arise from something deeper, perhaps information or entanglement. The truth is, we don't know which approach is correct. we might need a combination of insights from multiple approaches, or the answer might be something completely different that no one has thought of yet. Quantum gravity remains one of the biggest unsolved problems in physics, and solving it will likely require new experimental input. But how do you test quantum gravity? The energies where quantum gravity becomes important are the Planck scale, about 10 to the 19th power GeV. That's 15 orders of magnitude higher than what the Large Hadron Collider can achieve. We can't build accelerators that reach those energies, but we can look for indirect effects. Quantum gravity might produce subtle modifications to particle physics at lower energies. It might affect the propagation of light over cosmological distances, causing high-energy photons to travel slightly slower than low-energy ones. It might leave signatures in the cosmic microwave background or in gravitational waves from the early universe. Some experiments are already searching for these effects. Observations of distant gamma-ray bursts look for energy-dependent arrival times that would indicate quantum spacetime effects. Studies of the cosmic microwave background look for patterns that might reveal quantum gravity's role in inflation. Gravitational wave detectors are becoming sensitive enough to potentially see effects from quantum black hole horizons or other exotic phenomena. While we wait for experimental breakthroughs, theoretical work continues. Physicists are exploring the mathematical structures underlying quantum gravity, discovering surprising connections between seemingly unrelated areas of physics. The holographic principle, which suggests that the information content of any region of space can be encoded on its boundary, has emerged as a key insight. This principle connects black hole physics, quantum information theory, and the nature of spacetime in unexpected ways. The ADS/CFT correspondence, discovered by Juan Maldacena in 1997, provides a concrete example of holography. It shows that a quantum gravity theory in a certain type of curved space called anti-de Sitter space is mathematically equivalent to a quantum field theory without gravity living on the boundary of that space. This duality allows physicists to study quantum gravity by doing calculations in the equivalent boundary theory, which is often easier. The correspondence has led to insights about black hole information, quantum entanglement, and the emergence of space-time from more fundamental quantum degrees of freedom. While we work on the fundamental theory, experiments continue to test gravity in increasingly precise ways, looking for any deviation from general relativity's predictions that might point toward new physics. One approach tests the equivalence principle, the cornerstone of general relativity that says gravitational and inertial mass are identical. This principle has been tested to incredible precision, but there's always the possibility that at some level, different materials might fall at slightly different rates. The microscope satellite mission tested the equivalence principle to unprecedented precision, confirming that different materials fall at the same rate to within 1 part in 10 to the 15th power. That means if you drop two objects, one made of titanium and one made of platinum, and they fell for a year, they'd land within less than the width of an atom of each other. Other experiments look for fifth forces, hypothetical new forces that might exist alongside gravity. These could arise in theories with extra dimensions or new light particles. A fifth force might have a range of action different from gravity, becoming important only at certain distance scales. Experiments using torsion balances, atom interferometers, and gravitational wave detectors all search for signs of fifth forces. So far, no fifth forces have been detected, but the search continues with ever-improving sensitivity. Each negative result constrains theories and rules out certain possibilities. Tests of gravity also happen on cosmic scales. The orbits of planets provide sensitive probes of general relativity. NASA's Cassini spacecraft measured the curvature of spacetime near the Sun to incredible precision during its mission to Saturn. The spacecraft's radio signals were tracked as it passed behind the Sun, and the delay caused by spacetime curvature matched Einstein's predictions to extraordinary accuracy. Binary pulsars provide natural laboratories for testing gravity in extreme conditions. By timing pulsar pulses with millisecond precision over many years, astronomers can measure tiny changes in the orbit and compare them to general relativity's predictions. The agreement is perfect to within measurement uncertainties. The Event Horizon Telescope, which captured the first image of a black hole's shadow in 2019, is testing general relativity in some of the most extreme conditions in the universe. The image shows the supermassive black hole at the center of the galaxy M87, about 55 million light-years away. The black hole's shadow, a dark circle surrounded by a bright ring of emission from hot gas, has a size and shape that match general relativity's predictions. If gravity worked differently near black holes, the shadow would look different. The Event Horizon Telescope has also imaged the black hole at the center of our own galaxy, Sagittarius A star. Again, the observations match predictions. These observations are testing general relativity in regions where spacetime curvature is extreme, and so far, the theory holds up perfectly. Spacecraft missions routinely use gravity assists, also called gravitational slingshots, to gain speed without burning fuel. This technique beautifully demonstrates how gravity works in general relativity. When a spacecraft approaches a planet, it falls into the planet's gravitational well, following a curved geodesic. If the encounter is designed correctly, the spacecraft can emerge with more speed than it had initially, apparently gaining energy from nothing. The secret is that the planet is also moving through space, orbiting the Sun. The spacecraft steals a tiny bit of the planet's orbital energy. From the spacecraft's perspective, it's surfing the curvature of spacetime created by the moving planet. Voyager 2 used gravity assists from Jupiter, Saturn, Uranus, and Neptune to reach the outer solar system and eventually interstellar space with much less fuel than a direct route would require. The spacecraft's trajectory was carefully calculated to take advantage of the positions of the outer planets in what's called a grand tour. This alignment only happens about every 176 years. The Cassini mission used gravity assists from Venus twice, Earth once, and Jupiter once to reach Saturn. Each encounter boosted Cassini's speed and altered its trajectory, allowing it to reach Saturn with the limited fuel it could carry. The Juno mission used an Earth gravity assist to reach Jupiter, and the Parker Solar Probe uses Venus gravity assists to progressively lower its orbit closer to the Sun. These maneuvers require precise calculations of orbital mechanics and general relativity. Engineers must account for the curvature of spacetime around each planet and the spacecraft's trajectory through that curved geometry. A small error in the approach angle or speed can send the spacecraft off course by millions of kilometers. The fact that these missions work exactly as predicted, achieving their objectives with remarkable precision, is yet another confirmation that our understanding of gravity is correct. Every successful gravity assist is a practical demonstration of general relativity in action. Time dilation isn't just an exotic effect that happens near black holes or at high speeds. It's happening around you right now, though the effects are tiny for everyday situations. Your head ages faster than your feet because it's farther from Earth's center, experiencing slightly weaker gravity. Over a typical human lifetime of 80 years, your head ages about 90 nanoseconds more than your feet. You'd need incredibly precise atomic clocks to measure it, but it's real. If you live on a mountain, you age faster than someone living at sea level. Not by much, maybe a few extra microseconds over a lifetime, but it's measurable with modern atomic clocks. GPS satellites experience time dilation from two sources, and both must be accounted for. First, they're moving fast in their orbits, about 14,000 kilometers per hour. According to special relativity, moving clocks run slow, so this causes the satellite clocks to lose about 7 microseconds per day. But second, they're also higher up where gravity is weaker. According to general relativity, clocks in weaker gravity run faster, so this causes the satellite clocks to gain about 45 microseconds per day. The gravitational effect is larger, so overall, clocks on GPS satellites run about 38 microseconds per day, faster than clocks on the ground. If this wasn't corrected, GPS position errors would accumulate at about 10 kilometers per day. Within weeks, GPS would be useless for navigation, so the satellites continuously adjust their clock rates to compensate, sending time signals that are synchronized with ground clocks when they reach Earth's surface. Every time your phone shows your location on a map, it's using calculations that account for Einstein's general relativity. It's a routine reminder that gravity affects time, and we've understood this well enough to build working technology around it. In a very real sense, every time you use GPS navigation, you're testing general relativity and confirming its predictions. The fact that GPS works so reliably is strong evidence that our understanding of space-time and gravity is correct. Rotating massive objects don't just curve space-time. They drag it around as they spin, creating a kind of whirlpool effect in space-time itself. This is called frame dragging, or the lens-thurring effect, predicted by general relativity. For Earth, frame dragging is incredibly weak, but it's measurable. In 2004, NASA launched Gravity Probe B, carrying 4 ultra-precise gyroscopes. These gyroscopes were so perfectly spherical that if you scaled them up to Earth's size, the tallest mountains would be only about 2 meters high. The satellite orbited Earth for over a year, measuring tiny changes in the gyroscope's orientations caused by frame dragging. The experiment was extraordinarily difficult, requiring technology pushed to its absolute limits, but it succeeded, and the results confirmed Einstein's predictions. Earth's rotation does drag space-time around with it, and the gyroscopes detected that drag. Frame dragging becomes much more significant near rapidly rotating black holes. A black hole can have 3 properties: mass, electric charge, and angular momentum, which means it's spinning. Most black holes probably have little charge because charges attract opposites and neutralize. But angular momentum is different. If a star is rotating when it collapses, and all stars rotate at least a little, the resulting black hole will be spinning. Some black holes might spin at nearly the maximum rate allowed by general relativity, where the event horizon is rotating at nearly the speed of light. A spinning black hole drags space-time around it in a vortex. This creates an ergosphere, a region outside the event horizon, where space-time is being dragged so forcefully that nothing can remain stationary. You'd have to move along with the rotation, like being caught in a whirlpool. Inside the ergosphere but outside the event horizon, it's theoretically possible to extract energy from the black hole through a process called the Penrose process. You could drop an object into the ergosphere, have it split into 2 pieces, with one piece falling into the black hole and the other escaping. The escaping piece could emerge with more energy than the original object had, with the black hole losing angular momentum and slowing down. It sounds like science fiction, extracting energy from a black hole, but it's a legitimate consequence of general relativity. Whether any civilization could actually do this in practice is another question, but the physics allows it. General relativity allows solutions where space-time curves back on itself, creating closed time-like curves, paths through space-time that loop back to an earlier time. In principle, you could travel along such a path and arrive before you left, traveling into the past. This raises all the paradoxes associated with time travel. If you went back in time and prevented your own birth, would you still exist to go back? How can effects precede their causes? These logical problems have troubled physicists and philosophers for decades. The Gödel metric, found by mathematician Kurt Gödel in 1949, describes a rotating universe containing closed time-like curves everywhere. Wormholes, hypothetical tunnels through space-time connecting distant regions, might also permit time travel if one mouth moves fast enough relative to the other, creating a time difference between the two ends. Most physicists think closed time-like curves are probably impossible in the real universe. Perhaps quantum mechanics prevents them through some mechanism we don't yet understand. Perhaps the conditions needed to create them, like exotic matter with negative energy density, are physically unrealizable. Perhaps they exist, but anything trying to use them would be destroyed by quantum effects, with vacuum fluctuations becoming infinitely amplified near the time machine. Stephen Hawking proposed a chronology protection conjecture, suggesting that the laws of physics conspire to prevent time travel and avoid paradoxes. He joked that this is nature's way of making the universe safe for historians. General relativity doesn't forbid closed time-like curves outright, but their existence would create serious problems for our understanding of causality and the nature of time. Most physicists suspect that when we finally have a complete theory of quantum gravity, it will rule out closed time-like curves and time travel to the past. But we don't have that theory yet, so the question remains open. It's possible that time travel to the past is allowed by physics, just extraordinarily difficult or requiring exotic conditions that never occur in nature. Or it might be that closed time-like curves are simply impossible, forbidden by some deep principle we haven't discovered yet. Black holes create another deep puzzle at the intersection of gravity and quantum mechanics, the black hole information paradox. According to general relativity, anything that falls into a black hole is lost forever, trapped inside the event horizon with no way out. But according to quantum mechanics, information can't be destroyed. In quantum mechanics, the evolution of any system is reversible in principle. Given complete information about a system's quantum state at one time, you can calculate its state at any other time, forward or backward. Information is conserved. But if black holes destroy information, that fundamental principle is violated. This creates a contradiction that has puzzled physicists for decades. If black holes destroy information, quantum mechanics breaks down. If they preserve information, where does it go? How does information escape from inside the event horizon when nothing can escape? Stephen Hawking originally argued that information is genuinely lost, that black holes are the one place where quantum mechanics fails. This created an uproar in the physics community. Many physicists, particularly those working in quantum mechanics and particle physics, found this unacceptable because information conservation is such a fundamental principle. For decades, theorists battled over the paradox in papers, conferences, and famously heated debates. In the early 2000s, after decades of defending his position, Hawking conceded he was probably wrong and that information is somehow preserved. He proposed that information might be encoded in subtle correlations in the Hawking radiation emitted by black holes as they evaporate. But how exactly this works remains unclear. The mathematics of how information gets encoded in Hawking radiation and then released over billions of years as the black hole evaporates is extraordinarily complex and not fully understood. Recent work suggests the information might be encoded at the event horizon itself in a holographic manner. The holographic principle, which has emerged as a key insight in quantum gravity research, proposes that all the information about a three-dimensional volume of space can be encoded on its two-dimensional boundary, like a hologram where a 2D surface encodes 3D information. For a black hole, the horizon acts as this boundary. Every bit of information about everything that fell in might be preserved in subtle quantum states at the horizon, gradually released as the black hole evaporates through Hawking radiation over immensely long timescales. This would preserve unitarity, the quantum mechanical principle that information is never lost, but it requires quantum gravity to fully understand. And we don't have that complete theory yet. The information paradox remains one of the deepest puzzles connecting quantum mechanics, gravity, and the fundamental nature of information. Solving it will likely require insights that reshape our understanding of spacetime, quantum mechanics, or both. It's worth clarifying a common source of confusion because the terms sound similar but refer to completely different phenomena. Gravity waves, without ational, are oscillations in fluids caused by gravity trying to restore equilibrium. They're what you see when wind blows across water, creating waves on the surface. Gravity is trying to pull the water flat, but momentum carries the water past equilibrium, creating oscillations. You see gravity waves in clouds too, those beautiful rippling patterns called billow clouds. These have nothing to do with general relativity or Einstein's predictions. Gravitational waves with ational are ripples in spacetime itself, predicted by general relativity and detected by LIGO. They're produced by accelerating masses and travel at the speed of light, carrying energy away from their source. They're fundamentally different from any other kind of wave because they're oscillations in the fabric of space and time itself, not oscillations of matter or energy moving through space. The similar names cause endless confusion in popular media and even sometimes in scientific discussions, but they're entirely different phenomena with completely different physics. The bullet cluster provides one of the strongest and most visual pieces of evidence for dark matter. It's the aftermath of a collision between two galaxy clusters, about 3.8 billion light-years away. Galaxy clusters are the largest gravitationally bound structures in the universe, containing hundreds or thousands of galaxies, plus vast amounts of hot gas between the galaxies. When two clusters collide, which happens over millions of years as they pass through each other, the hot gas in each cluster interacts electromagnetically. The gas particles collide, creating shock waves and heating to hundreds of millions of degrees. This causes the gas to slow down and stay near the collision site, radiating X-rays that we can detect with space telescopes. But gravitational lensing reveals something remarkable. When we map where the mass actually is, by studying how the cluster bends light from background galaxies, we find that most of the mass traveled with the clusters themselves, not with the gas. The mass, visible through gravitational lensing, passed right through without slowing down. This is exactly what you'd expect if dark matter exists and barely interacts with normal matter. The dark matter in each cluster, which makes up most of the mass, passed right through the collision without interacting or slowing down. Meanwhile, the normal matter, the hot gas, collided and stayed behind. We can see this directly in images. X-ray images show where the hot gas is, while gravitational lensing maps show where the mass is, and they're in different places. Alternative theories of gravity, which attempt to explain galactic rotation curves without invoking dark matter by modifying how gravity works on large scales, struggle to explain the bullet cluster. These theories, like MOND for modified Newtonian dynamics, predict that gravitational effects should follow the distribution of normal matter. But in the bullet cluster, the gravitational effects clearly follow the dark matter, not the visible gas. This observation strongly supports the idea that dark matter is real stuff, actual particles of some kind, not just a modification of how gravity works. Light climbing out of a gravitational well loses energy because of how space-time curvature affects photons. For light, energy is directly related to frequency through Planck's constant. Lower energy means lower frequency and longer wavelength. For visible light, this shifts the color toward the red end of the spectrum, hence the name gravitational redshift. The effect is small in weak gravitational fields, but becomes significant near massive compact objects. Light from our sun shows a small but measurable gravitational redshift compared to the same atomic transitions measured in laboratories on Earth. The effect is tiny, only about 2 parts per million, but it's been measured precisely. Light from white dwarf stars, which pack about the Sun's mass into an Earth-sized volume, shows much larger redshifts, reaching up to about 50 parts per million. Light from neutron stars, even more compact, with about 1.4 solar masses in a sphere just 20 kilometers across, is redshifted by roughly 30%. These observations directly test general relativity's predictions about gravitational time dilation, because the gravitational redshift is really a manifestation of time passing at different rates at different positions in the gravitational field. Near a black hole's event horizon, the redshift becomes extreme. Photons barely escaping the horizon lose so much energy that they shift to infinitely long wavelengths, becoming effectively undetectable. An outside observer watching something fall toward a black hole sees it becoming dimmer and redder, fading into invisibility as it approaches the horizon. Gravitational redshift also appears cosmologically and has been observed on the grandest scales. As the universe expands, light traveling through space gets stretched along with the expansion. The wavelength increases proportionally to how much the universe has expanded since the light was emitted. By measuring how much a distant galaxy's light has been redshifted, astronomers can determine its distance and how long ago that light was emitted. This is why astronomers talk about redshift as a proxy for distance and time. A galaxy at redshift 1 has its light stretched by a factor of 2, meaning the universe has doubled in size since that light was emitted. A galaxy at redshift 9 has its light stretched by a factor of 10, meaning we're seeing it as it was when the universe was only 1/10 its current size. The cosmic microwave background, the afterglow of the Big Bang, has been gravitationally redshifted dramatically by the universe's expansion over 13.8 billion years. This radiation was emitted as visible and infrared light when the universe was only 380,000 years old and had a temperature of about 3,000 Kelvin. Since then, the universe has expanded by a factor of about 1,100, stretching the wavelengths by the same factor. What was once visible light has been stretched into microwaves with a temperature of 2.7 Kelvin. This is direct evidence that the universe has been expanding and cooling over cosmic time. The cosmic microwave background is the oldest light we can see, a baby picture of the universe from when it was only 380,000 years old. Before that moment, the universe was so hot and dense that it was opaque, a glowing plasma where photons constantly scattered off free electrons. But as the universe expanded and cooled, electrons combined with protons to form neutral hydrogen atoms. Suddenly, photons could travel freely through space without constantly scattering. The universe became transparent, and those photons have been traveling ever since, carrying information about the early universe across billions of light years and billions of years of time. The CMB isn't perfectly uniform. It has tiny temperature variations, about 1 part in 100,000. These variations reflect density variations in the early universe, slight ripples that gravity then amplified over billions of years into the galaxies and clusters we see today. By studying the pattern of these variations in exquisite detail, cosmologists can test theories of gravity, measure the universe's properties with incredible precision, and trace the evolution of cosmic structure from the earliest times. Satellites like COBE, WMAP, and Planck have mapped the CMB with increasing precision, revealing a universe that matches the predictions of general relativity and the Big Bang model beautifully. The CMB also shows potential evidence of gravitational waves from the very early universe. During inflation, the hypothesized period of exponential expansion in the first tiny fraction of a second after the Big Bang, gravitational waves would have been produced by quantum fluctuations. These primordial gravitational waves would have left a distinctive pattern in the CMB's polarization, a characteristic curl pattern called B modes. Future experiments hope to detect this pattern, which would be direct evidence of inflation and quantum gravity effects at work during the universe's first moments. Detecting primordial gravitational waves would open a window on physics at energy scales far beyond what any particle accelerator could ever achieve. While general relativity has passed every test with flying colors, some physicists continue to explore modified theories of gravity. These modifications might explain puzzling observations without requiring dark matter or dark energy, or they might reveal new physics in regimes we haven't fully tested yet. MOND, modified Newtonian dynamics, proposes that gravity behaves differently at extremely low accelerations, like those experienced by stars in the outer parts of galaxies. At these tiny accelerations, gravity might become stronger than Newton's or Einstein's theories predict. This could potentially explain why stars orbit faster than expected based on visible matter, without invoking dark matter. MOND has had some successes, predicting certain galaxy rotation curves quite well, but it struggles to explain other observations. It doesn't account for gravitational lensing as well as dark matter does. It can't explain the bullet cluster, where gravitational effects are clearly offset from the visible matter. And it doesn't have a fully developed relativistic version that works as well as general relativity in all its predictions about time dilation, gravitational waves, and black holes. Most physicists consider MOND an interesting idea that ultimately doesn't match the full range of observations as well as dark matter plus general relativity does. Other theories modify general relativity more directly, adding new terms to Einstein's equations, or introducing extra fields that couple to gravity. Some theories, like FR gravity, modify the mathematical form of Einstein's equations. Others introduce scalar fields, additional quantum fields that interact with gravity and might account for dark energy. Some theories propose that gravity becomes stronger or weaker on certain scales, potentially explaining cosmic acceleration without dark energy. These theories face a high bar. They must explain not just one puzzling observation, but all of them. Galactic rotation curves, gravitational lensing, the CMB, cosmic expansion history, black holes, gravitational waves, and all the other phenomena that general relativity handles successfully. So far, no modified theory matches general relativity's track record. General relativity explains an enormous range of phenomena with remarkable precision, from the precession of Mercury to gravitational waves from colliding black holes, all with the same set of equations Einstein wrote down over a century ago. Any new theory must do everything general relativity does, plus explain whatever new phenomena motivated the modification, without introducing problems elsewhere. That's an extremely difficult challenge, which is why general relativity remains the standard theory of gravity, despite intensive efforts to find alternatives. But the search continues, because if dark matter or dark energy turn out to be illusions caused by our incomplete understanding of gravity, modified theories would be the solution. And even if dark matter and dark energy are real, studying modified theories helps us understand what aspects of general relativity are essential and what might be modified in a more complete theory that includes quantum mechanics. In quantum field theory, forces are mediated by particles. Electromagnetism is carried by photons, particles of light. The strong nuclear force that holds atomic nuclei together is carried by gluons. The weak nuclear force responsible for certain types of radioactive decay is carried by W and Z bosons. If gravity is quantized in the same way as these other forces, it would be carried by gravitons, hypothetical particles that have never been detected. Gravitons would be massless, like photons, and travel at the speed of light. Unlike photons, gravitons would interact with all forms of energy and mass, not just electric charges. But there's a fundamental problem with this approach. When physicists try to calculate processes involving gravitons using the same methods that work brilliantly for other forces, they get nonsensical results. The calculations give infinities that can't be removed through standard techniques. For other forces, We can absorb infinities into the definitions of particle masses and charges through a process called renormalization, arriving at finite predictions that match experiments beautifully. But for gravity, this doesn't work. The technical term is that gravity is non-renormalizable. The infinities get worse at higher energies, suggesting the theory breaks down at some scale. Probably the Planck energy, where quantum gravity effects become as important as gravity itself. This is why we need a new approach to quantum gravity. The straightforward method of treating gravity like other quantum forces doesn't work. Something fundamentally different is needed, which is why physicists have developed radically new approaches like string theory, loop quantum gravity, and others. These theories don't just quantize gravity in the usual way. They reconceptualize what gravity is at the most fundamental level. The Planck scale represents the limit of our current understanding, where quantum effects and gravitational effects become equally important. It's determined by combining fundamental constants from different areas of physics, the speed of light from relativity, Newton's gravitational constant from gravity, and Planck's constant from quantum mechanics. When you combine these in the right way, you get natural units for length, time, mass, and energy at which quantum gravity must be important. The Planck length is about 10 to the minus 35 meters, astonishingly tiny. For comparison, a proton is about 10 to the minus 15 meters, and an atom is about 10 to the minus 10 meters. The Planck length is 20 orders of magnitude smaller than a proton. The Planck time is about 10 to the minus 43 seconds, the time it takes light to travel one Planck length. The Planck energy is enormous in particle physics terms, about 10 to the 19th power giga-electronvolts, far beyond what any conceivable particle accelerator could achieve. The Large Hadron Collider reaches energies of about 10,000 giga-electronvolts, still 15 orders of magnitude below the Planck energy. At the Planck scale, quantum effects of gravity become as important as gravity itself. Space-time probably becomes foamy, with quantum fluctuations creating a chaotic structure where our usual notions of smooth space-time break down. Virtual black holes might constantly appear and disappear. The very concepts of distance and time might lose their usual meanings. Some physicists think space-time itself is an approximation that emerges from something more fundamental, like information or quantum entanglement, only becoming a useful concept above the Planck scale. We can't directly probe the Planck scale experimentally. The energies required are impossibly high, and even if we could somehow concentrate that much energy in a small region, we'd create a black hole. But we can look for indirect effects. Quantum gravity might produce tiny modifications to particle physics at lower energies. It might affect how light propagates over cosmological distances, causing high-energy photons to travel slightly slower than low-energy ones. An effect called Lorentz invariance violation. It might leave signatures in gravitational waves or in the cosmic microwave background. Experiments are searching for all these effects with increasing sensitivity, and so far, they've found nothing, which constrains possible theories of quantum gravity. Some physicists think gravity might not be fundamental at all, but rather an emergent phenomenon arising from something deeper. In the 1990s, Ted Jacobson showed that Einstein's equations can be derived from thermodynamic principles, the physics of heat and entropy. He showed that if you apply the laws of thermodynamics to horizons, like event horizons of black holes, or the apparent horizon you see when you accelerate, you get Einstein's equations. This suggests gravity might be fundamentally a thermodynamic phenomenon, like temperature or pressure, rather than a fundamental force. More recently, Eric Verlinde proposed entropic gravity, suggesting that what we call gravity is actually the result of an entropic force, a tendency for systems to evolve towards states with higher entropy. In this view, the apparent attraction between masses isn't caused by gravitons or curved spacetime, but by changes in information and entropy at a microscopic level. If gravity is emergent, it would explain why it's so difficult to quantize. You don't quantize temperature or pressure directly. They emerge from the quantum behavior of underlying particles. Similarly, spacetime and gravity might emerge from some more fundamental quantum description, perhaps involving quantum entanglement or quantum information. This is highly speculative, and the details remain controversial. Many physicists are skeptical of emergent gravity ideas because they struggle to reproduce all of general relativity's predictions. But it's an intriguing possibility that represents a completely different way of thinking about gravity. Instead of trying to quantize general relativity directly, maybe we should recognize that gravity and spacetime are approximate concepts that emerge at large scales from some deeper quantum description. If true, this would be a profound shift in our understanding, comparable to realizing that temperature emerges from molecular motion, or that solidity emerges from electromagnetic forces between atoms. Roger Penrose has proposed a controversial and fascinating idea connecting gravity to consciousness, suggesting that quantum states in the brain might collapse due to gravitational effects, and this collapse might be related to moments of conscious experience. The idea is that neurons contain structures called microtubules, cylindrical protein structures that help maintain cell shape. Penrose, working with anesthesiologist Stuart Hameroff, proposes that these microtubules can exist in quantum superpositions of different states. When the superposition involves enough mass-energy difference to create significant spacetime curvature differences, gravity causes it to collapse spontaneously, creating a discrete moment of conscious awareness. This theory, called orchestrated objective reduction, or ORC, is highly controversial. Most neuroscientists are skeptical because the brain seems too warm and noisy for delicate quantum states to survive long enough to play a functional role. Quantum coherence typically requires very cold temperatures and careful isolation from the environment, conditions that certainly don't exist in living brain tissue. But Penrose argues that if consciousness involves quantum processes that collapse due to gravity, it would explain why we experience consciousness as a series of discrete moments rather than a completely continuous flow, and why conscious experience seems to involve a unity of information that might require quantum entanglement. The theory makes some testable predictions about how anesthetics work and about quantum processes in brain tissue. So far, experimental evidence is mixed and inconclusive. Some studies have found evidence of quantum effects in microtubules, but whether these are relevant to consciousness remains unproven. Most physicists and neuroscientists remain skeptical, but the ideas can't be dismissed entirely. If there's any connection between quantum mechanics, gravity, and consciousness, it would be one of the most profound discoveries in science. Whether gravity plays a role in consciousness remains highly speculative, but it's an example of how gravity, even after centuries of study, continues to inspire radical new ideas that challenge our understanding of reality. Where is gravity research headed? Several exciting frontiers are being actively explored. Space-based gravitational wave detectors like LISA will open a new window on the universe. LISA will be sensitive to much lower frequency gravitational waves than LIGO, detecting waves from supermassive black hole mergers at the centers of galaxies, binary white dwarf stars in our galaxy, and possibly even gravitational waves from the Big Bang itself. These observations will test general relativity in new regimes and might reveal unexpected phenomena. Improved tests of the equivalence principle might reveal tiny violations that point toward new physics beyond general relativity. Experiments in space, away from Earth's gravitational field and vibrations, can achieve unprecedented precision, potentially detecting deviations from general relativity at levels of 1 part in 10 to the 18th power or better. Black hole imaging will improve dramatically as the Event Horizon Telescope expands. More radio telescopes are joining the network, and future space-based telescopes might directly image black holes in even greater detail. These observations might show matter spiraling into black holes in real time, test the detailed predictions of general relativity near event horizons, measure black hole spins with extreme precision, and possibly detect exotic phenomena like naked singularities if they exist, though most physicists expect they don't. Quantum gravity experiments are becoming more sophisticated. Researchers are testing quantum superpositions with increasingly massive objects, probing where quantum behavior gives way to classical behavior. Some experiments look for quantum interference effects with molecules containing thousands of atoms. Others propose using optically trapped mirrors to test quantum superposition of mesoscopic objects. These experiments might reveal where gravity becomes important in collapsing quantum superpositions, potentially pointing toward the correct theory of quantum gravity. Dark matter searches continue with ever greater sensitivity. New detectors underground with improved shielding and larger target masses are looking for rare collisions between dark matter particles and normal atoms. Particle physics experiments at accelerators are searching for dark matter produced in collisions. Astronomical surveys are mapping dark matter's distribution with unprecedented precision using gravitational lensing, and new theoretical ideas about what dark matter could be, from ultralight axions to primordial black holes to dark photons, are motivating new experimental approaches. Dark energy investigations aim to determine whether it's truly constant or evolving over time. Large surveys mapping millions of galaxies measure cosmic expansion history in unprecedented detail. The Dark Energy Survey, the Euclid Space Telescope, and the upcoming Vera Rubin Observatory will provide increasingly precise measurements of how the expansion rate has changed over cosmic history. If dark energy is not constant, these observations might reveal how it evolves and provide clues about its fundamental nature. Gravitational wave cosmology will use waves from the early universe to probe conditions at energies far beyond particle accelerators. Detecting primordial gravitational waves in the cosmic microwave background would reveal physics from when the universe was only 10 to the minus 35 seconds old, providing information about energy scales 15 orders of magnitude higher than the Large Hadron Collider can reach. This would be an extraordinary achievement, essentially using the entire universe as a laboratory to study physics at quantum gravity scales. So what does all this understanding of gravity mean for you personally? For most of your daily life, gravity's effects beyond keeping you on the ground are too small to notice. You probably don't think about time dilation when you climb stairs, or about space-time curvature when you throw a ball. But understanding gravity changes how you see reality at a fundamental level. You're not standing on a motionless platform being pulled downward by an invisible force. You're following a geodesic through curved four-dimensional space-time, constantly accelerating upward through space-time because electromagnetic forces from the ground prevent you from following your natural path toward Earth's center. When you drop something, you're not seeing a force pull it down. You're seeing it follow the geometry of space-time, moving along the straightest possible path through a curved geometry. The object isn't accelerating from its own perspective. It's in free fall, following its natural trajectory through space-time. You're the one accelerating, held in place by forces from the ground. When you look up at the moon, you're not seeing an object held in place by an invisible tether. You're seeing an object in perpetual freefall, following a geodesic that loops around Earth because Earth's mass curves space-time. The moon is constantly falling toward Earth, but also moving sideways fast enough that it keeps missing. That's the beauty of an orbit. Every moment of your life, you're interacting with the fundamental geometry of the universe. You're surfing the curvature of space-time created by Earth, the Sun, the galaxy, and all the mass energy in the observable universe. Distant galaxies billions of light years away curve space-time around them, and that curvature, however minutely, affects you. You're part of a vast cosmic web of gravitational interactions connecting everything in the universe. That's not poetic exaggeration. That's literal truth according to our best understanding of physics. Perhaps the deepest lesson from studying gravity is this: reality is not what it seems. Our everyday intuitions, built from evolution in Earth's environment over millions of years, can be profoundly misleading about how nature actually works at its most fundamental level. For thousands of years, it seemed obvious that the Earth was flat and stationary. Our senses told us so. It seemed obvious that heavy objects fall faster than light ones. Common experience suggested it. It seemed obvious that the sun revolves around the Earth. We can see it moving across the sky. All of these obvious facts turned out to be completely wrong. Gravity seemed like a force pulling objects together, an invisible string connecting masses. Wrong. It's the curvature of space-time, a geometric property of the four-dimensional fabric of reality. Space and time seemed like separate, absolute things, providing a fixed stage for events. Wrong. They're woven together into space-time, and both are relative to the observer, flexible and dynamic, rather than rigid and absolute. Understanding gravity required letting go of intuition and following the mathematics wherever it led, even when it pointed towards strange conclusions like curved space-time, time dilation, and black holes from which nothing can escape. The same pattern appears throughout physics. Quantum mechanics tells us that particles don't have definite positions until they're measured, existing instead in probabilistic superpositions of many possible states. That violates common sense entirely. Special relativity tells us that simultaneity is relative, that events that happen at the same time for one observer happen at different times for another. That contradicts our everyday experience of time. These ideas violate common sense, yet they're unquestionably correct, confirmed by countless experiments and incorporated into working technology. The universe doesn't care about our intuitions. It operates according to its own rules, and those rules are often surprising, counterintuitive, and strange. The joy and challenge of science is discovering what those rules actually are, not what we wish them to be, or what our intuition suggests they should be. Despite how much we've learned about gravity over the past few centuries, from Newton's apple to Einstein's curved space-time to LIGO's detection of gravitational waves, profound mysteries remain. What is dark matter? We know it's there from its gravitational effects on galaxies, clusters, and the entire universe, but we don't know what it's made of. Is it a new kind of particle? Multiple types of particles forming a whole dark sector of physics? Primordial black holes? Something even stranger? We don't know. What is dark energy? Why does it exist? Why does it have the value it does? Is it truly constant, or does it evolve over time? Why is it so much smaller than quantum mechanics predicts? These questions touch on the deepest aspects of our universe, and we don't have answers. How do we reconcile gravity with quantum mechanics? What happens at the Planck scale where both become equally important? Is space-time fundamental, or does it emerge from something deeper? Do strings exist? Are there extra dimensions? Is quantum gravity an emergent phenomenon? These questions are crucial because black holes and the Big Bang, two of the most important phenomena in the universe, require quantum gravity to fully understand. What really happens inside black holes? Is there truly a singularity with infinite curvature, or does quantum gravity prevent that? What happens to information that falls into a black hole? How is it preserved and eventually released? Can we detect signatures of quantum gravity in black hole observations? Did cosmic inflation really happen? Can we detect direct evidence of it through primordial gravitational waves? What caused inflation? What is the inflaton field that drove exponential expansion? Why did inflation end when and how it did? Are there other universes beyond our own? Is our cosmos just one bubble in an eternally inflating multiverse? If so, can we ever find evidence of other universes? Or is the multiverse idea untestable and therefore not science? These questions touch on the ultimate nature of reality and our place in it. Why is gravity so weak compared to other forces? Is there a deeper reason for the hierarchy problem? Are there extra dimensions that we can't directly observe? Is there new physics at high energies that explains the weakness of gravity? Why does the Higgs boson have the mass it does instead of being much heavier? Can we detect quantum effects of gravity? Will we ever observe a graviton? Can we see quantum superpositions of space-time itself? These questions drive current research, and the answers, when we find them, will likely surprise us as much as curved space-time surprised people a century ago when Einstein first proposed it. The story of gravity is far from over. It's an ongoing narrative where every answer raises new questions, and every solved mystery reveals deeper mysteries beneath. Newton gave us the first mathematical description of gravity, showing that the same force governs both falling apples and orbiting planets. That insight unified terrestrial and celestial physics, showing the universe is comprehensible through mathematics and reason. Einstein revealed that gravity isn't a force, but the curvature of space-time itself. This insight unified space, time, matter, and energy into a single geometric framework. It showed that reality is stranger, more beautiful, and more interconnected than we ever imagined. Modern researchers are pushing further, detecting gravitational waves from colliding black holes billions of light years away, imaging black hole shadows with radio telescope networks spanning the globe, mapping dark matter's distribution through gravitational lensing, measuring cosmic expansion with unprecedented precision, and searching for the quantum theory of gravity that will unite general relativity and quantum mechanics into a complete description of nature. Each generation of physicists builds on the work of the last, standing on the shoulders of giants and looking further. We've come remarkably far from Newton watching apples fall in his garden, but we also know our understanding is incomplete. Future generations will look back on our time and see both what we got right and what we missed. They'll discover things we can't yet imagine, just as we've discovered things Newton couldn't imagine. Black holes, gravitational waves, dark energy, quantum mechanics. None of these were conceivable in Newton's time. What revolutionary concepts await discovery that we can't even formulate questions about yet? That's the beauty of science. It's not a collection of final answers written in an unchanging textbook. It's an ongoing conversation with nature, a process of continual refinement where each era builds on the last, sometimes confirming previous ideas, sometimes overturning them, always learning. And gravity, the most familiar force in our daily lives, the force we experience every moment simply by existing on Earth's surface, remains at the center of that conversation. After centuries of study, after being described by Newton's equations, reinterpreted by Einstein's geometric vision, confirmed by countless experiments from Mercury's orbit, to gravitational waves to GPS satellites, gravity still reveals new surprises, still raises profound questions, still connects to the deepest mysteries about the nature of space, time, matter, energy, and the universe itself. We began this journey by asking what gravity really is. We've seen that it's not the simple downward pull we experience every day, though that's how it manifests in our daily lives. It's something far more profound. The curvature of space-time itself, a fundamental property of the four-dimensional fabric that makes up our universe. We've traced gravity's story, from Newton's universal law, through Einstein's geometric revolution to modern discoveries of gravitational waves and cosmic mysteries like dark matter and dark energy. We've explored black holes where spacetime curves so severely that nothing escapes, and we've considered quantum gravity where our current theories break down and new physics is needed. Along the way, we've seen that understanding gravity means understanding the cosmos itself. Gravity shapes the motion of planets, the evolution of stars, the structure of galaxies, the expansion of the universe, and the flow of time. It's woven into every aspect of physical reality. But we've also seen that much remains unknown. Gravity continues to surprise us, revealing new phenomena and raising new questions with each discovery. The search for a complete understanding continues, driven by human curiosity and the desire to know how the universe really works. If you've made it this far, thank you for joining this deep exploration into one of nature's greatest mysteries. Understanding gravity doesn't change your daily life in obvious practical ways, but it does fundamentally change how you see the world and your place in it. You're not just a person standing on a planet held down by an invisible force. You're a conscious being made of atoms forged in stellar cores, existing in a specific moment of cosmic history, moving through curved four-dimensional space-time in a universe that's both stranger and more wonderful than common sense could ever suggest. The next time you feel your weight, remember you're experiencing the resistance of electromagnetic forces, preventing you from following your natural geodesic through space-time. When you watch something fall, remember you're seeing it follow the geometry of curved space-time. When you look up at the night sky, remember that every photon reaching your eyes has traveled through curved space-time, carrying information across vast distances and vast spans of time. You're part of something much larger than yourself, connected through gravity to everything else in the universe. That understanding, that shift in perspective, from seeing gravity as a simple downward pull to understanding it as the fundamental geometry of space-time, is itself a kind of journey. It's a journey from everyday experience to profound truth, from surface appearance to deep reality, from isolation to connection. And that journey, like gravity itself, connects us all, not just to Earth, but to the cosmos, to the long history of scientific discovery, to the ongoing quest to understand nature at its most fundamental level. We're privileged to live in a time when we can pursue that understanding, when we have the tools to detect gravitational waves, image black holes, and probe the deepest questions about space, time, and gravity. The journey continues, and you're part of it simply by asking questions, seeking understanding, and marveling at how strange and beautiful reality turns out to be.